So onto the MIT integration big qualifying exam 2014 problem 20, and this is the last problem, which is the definite integral from x equals to 0 to x equals to pi over 2 of 1 over 2 plus cosine x. So this is actually a tricky problem, and we are going to see how we may be able to solve this. So this is our problem, x from x equals to 0 to x equals to pi over 2 of 1 over 2 plus cosine x. I like to plot this, focus on cosine x, right? So from pi over 2 to pi to 3 pi over 2 to 2 pi to 5 pi over 2, right? This is 1. So the curve goes to 0 here, goes to maximum, comes back to 0, and goes to maximum, and then comes back to 0. And so that means that when cosine x is 1, that becomes 1 over 3, so we get a minimum here, and this goes out until it's a maximum here, and it comes up to a minimum here, and then it becomes, it continues like that, right? Until it's a maximum here. But as we can see, the integral here, we have to separate it into two domains. So we have the domain from 0 to 2 pi, and we see this next domain here is repetitive, is the same as, so these two domains are the same, right? So what we're going to do is we're going to split our integral into two. So we're going to say this is equals to 0 to 2 pi plus 0 to pi over 2. Those are our two domains that we're going to focus on. So this is a complete cycle. From 0 to pi is a complete cycle, and then we begin another cycle. So 0 to 2 pi over 2 plus cosine x plus 0 to pi over 2 . And we can now express this into a half angle formalism, because cosine x is the same cosine squared x over 2 minus 1. 2 over 2 plus 2 cosine squared x over 2 minus 1, which is equals to pi 2 cosine squared x over 2 plus 0 to pi over 2 over 2 plus 2 cosine x over 2. So the first substitution we're going to do is we're going to let t be equal to tan x over 2, so that dt dx is equals to a half sec x over 2, and that means that 2 dt over sec squared x over 2 is equals to dx, which means that 2 dt is equals to 1 plus tan squared x over 2 is equals to dx, and this x over 2 is tan x squared x over 2 is t, so 2 dt over 1 plus t squared is going to be our next substitution. We had two integrals, the integral from 0 to 2 pi of x over 1 plus 2 cosine x over 2. And then we're going to maybe call our next integral 0 to pi over 2. So let's try to do the limits, right? So we said t is equal to tan x over 2. So for the yellow integral, we have x, we have t, we have 0, and then we have 2 pi, right? And we might have to split our integral into two, because we saw that it was symmetric. So what we can do is we can go ahead and say that instead of that, we're going to say that this is twice the integral from 0 to pi, and so our limit from 0 to pi would mean that we have from 0 we have 0, and here so if we have tangent, we have asymptotes, right? Pi over 2, so something like that. So this tends to infinity at pi over 2. And for the blue integral, we have x and t, 0, pi over 2. From 0 is 0. At pi over 2, which is tangent of pi over 2 over 2, which is pi over 4, this becomes 1. And so we have interesting limits, but also what's key here is you have a triangle x over 2, right? And tangent is opposite over adjacent, so the hypotenuse becomes square root of 1 plus t squared. So cosine squared x over 2 is the same as 1 over 1 plus t squared, because it's 1 over square root of 1 plus t squared, which is 1 over t squared. So our integral becomes 0 to 2 pi dx over 1 plus 2 cosine squared x over 2 plus the blue integral, which is 0 to pi over 2 dx 1 plus 2 cosine squared x over 2. We saw that from the plot we had, from x equals to 0, pi to pi, 1 over 2 plus cosine x started from a third, and you go up to the maximum, and then up to minimum there. And as we can see, this part here is the same as this part. So our integral, this integral here becomes twice the integral from 0 to pi of dx 1 plus 2 cosine squared x over 2 plus 0 to pi over 2 dx over 1 plus 2 cosine squared x over 2. Okay. And so, since we had said t equals to tan x over 2, let me go back to the yellow. If you have the triangle here, x over 2, tangent is opposite, so t over adjacent 1, and therefore the hypotenuse is 1 plus t squared. So cosine squared x over 2 is equals to be the square of 1 over root adjacent over hypotenuse 1 plus t squared, right? Which is equals to 1 over 1 plus t squared. And so our integrals twice 0 to pi of dx over 1 plus 2 cosine squared x over 2 plus the blue integral, which is 0 to pi over 2 dx over 1 plus 2 cosine squared x over 2 is the same as 2, and we got to look at the limit here, right? So when x is 0, let's say when we have x and t, x is 0, tan 0 over 2 is 0, x is pi, tan pi over 2, as x tends to pi over 2, t will tend to infinity, right? So now we have 0 to infinity of 2 dt over 1 plus t squared over 1 plus 2 cosine squared x is 1 over 1 plus t squared plus 0, and the limits here we see that x t as 0 0, pi over 2, tangent of pi over 2 is 1, so 1 over 2 dt over 1 plus t squared over 1 plus 2 1 plus t squared. Okay, so it becomes 2 0 pi of 8 2 dt over 1 plus t squared 3 plus t squared over 1 plus t squared. This and that will cancel, plus the same vein, we'll just write the same thing, 0 to 1, 2 dt over 1 plus t squared over 3 plus t squared over 1 plus t squared. This and that would cancel, right? So we now have an integral, very interesting, of 2 0 to infinity of 2 dt over 3 plus t squared plus and 0 to 1 2 dt over 3 plus t squared. Okay, so becomes 4 0 dt over 3 plus t squared plus 0 to 1 2 dt over 3 plus t squared. So we can do another quick substitution by letting t be equal to root 3 tangent theta, so that dt d theta is equal to root 3 sec square theta, and therefore dt can be right, and then as we have limits, we have t and we have theta, And so when 0, as it tends to theta, arctangent of 0 is going to be 0. Arctangent of, as t tends to infinity, we get pi over 2. Right? And then for the blue integral, t theta 0 equals 0, and then as at 1 we get pi over 6. Okay, so we have, since we have to integral 0 to infinity of dt over 3 plus t squared plus twice integral from 0 to 1 dt over 3 plus t squared, and then we have now 4, 0, limit pi over 2, dt happens with root 3 sec square theta d theta over 3 plus 3 tan square theta plus this is 2, 0, pi over 6 root 3 sec square theta d theta over 3 plus 3 tan square theta. So this becomes 4 root 3 over 3, 0, pi over 2 sec square theta over 1 plus tan square theta d theta plus twice root 3 over 3, 0, pi over 6 sec square theta theta 1 plus tan square theta. Now what is key here is we know that 1 plus tan square theta is sec square theta, so this and that would cancel, this and that would cancel. So let me just use blue for consistency's sake, and that would cancel. So we come to a point where we have 4 root 3 over 3, 0, pi over 2 theta plus 3 over 3, 0, pi over 6 d theta. So this is 4 root 3 over 3 theta 0 pi over 2 2 root 3 over 3 theta 0 pi over 6. Okay, so as we proceed, we come to 4 root 3 over 3. Pi over 2 minus 0 is just going to be pi over 2. So this one, this goes twice. And then we have that, which is 2 root 3 over 3 times pi over 6. So 1, 3. Okay. So equals to 2 root 3 over 3 pi plus root 3 over 9 pi. So let's just merge everything there, and so we get 9 as our denominator, and so 9 divided by 3 is 3. 3 times 2 is 6 root 3 pi plus root 3 pi, and this becomes 7 root 3 over 9 pi. So our problem that started as a very benign problem is equal to 7 root 3 over 9 pi. That's the answer.